the water that comes out of your cold water tap, when you turn on the faucet, out streams water that fell as precipitation in the mountains 25 kilometers east of here, some 180 years ago. It has been filtered through tens of layers of lava film, and then they have boreholes about 2.5-3 miles out that they drill down to about 150 meters, and that's where it springs forth. They pump it up and pipe it into the cold water system of the city and the adjacent municipalities. So even if it's almost 2 centuries old, it's absolutely fresh. It's pure. And you can do the taste test if you already bought bottled water and see which you like better, the water from the bottle or the water from the faucet. Don't confuse it with the hot water faucet. You really shouldn't in the capital, because in the hot water faucet you will find geothermal water coming directly from the ground, about 2,000 meters in depth. But it has a tiny part of sulfur, and it does smell. It's harmless to drink it, but it doesn't taste very nice. So you can't really go wrong on that. You can't mistake what is cold and what is hot. The hot water is also used for house heating. It is delivered to the houses at 80 degrees centigrade, but most of the hotels now bring that temperature down by blending it with fresh water down to between 60 and 40 degrees. There have been some people have been burning themselves because they were unaccustomed to water that was 80 degrees hot. So this was a safety measure. So like I said, the houses are heated with geothermal energy, hot water directly from the ground, and this is the same case in most of the country. 97% of all housing in Iceland is heated by geothermal energy. The remaining 3% are heated by electricity, so there is no use of fossil fuel for house heating in Iceland. And this is really a boon to our economy, not having to import oil or coal. A few words about Iceland. Iceland is on the Atlantic ridge that reaches from the Arctic to the Antarctic. Iceland is the only part of the ridge that is above sea level, and this is due to plume in the mantle that rises from more than 2,000 kilometers depth up towards the surface. And this is also the driving force driving the continents of North America and Eurasia apart by about an inch a year. It doesn't happen, that is on average, it doesn't happen like 1 inch every year. It happens in spurts. And therefore also Iceland is expanding by an inch a year on average. And the rifts are partly filled from below by the magma coming from the mantle. But sometimes the magma reaches the surface and you have a volcanic eruption. There are 300 active volcanoes in Iceland, and we have a volcanic eruption on average every 6 years. The last one was less than 3 years ago. The one before that was in 2011, and the one before that was in 2010. So you might remember that one in 2010 because that was a volcano under a glacier that melted the glacier off the top and when the meltwater and the magma met, there was an explosion turning the lava into ash that rose into the atmosphere, high into the atmosphere, and shut down the air traffic over the North Atlantic and Europe. Many people were stranded at the airport for 3 days. Iceland is on the between the 64th and the 66th parallel, so it's pretty far north. Almost it touches the Capricorn, and there's one island that belongs to Iceland that is north of the Capricorn. But still we are here now in January, and it's above freezing. And that is because the Icelandic weather is shaped by two deciding factors. One is the effects of the sea, because it's an island, and the sea is usually warmer than the land during the night, and the nights are long in Iceland. So the effects of heat transfer from the seas are quite, there's quite a lot of this effect of the heat transfer, but we have an addition of heat transfer. That is the Gulf Stream that comes from the Gulf of Mexico, streams up the eastern seaboard of North America, cuts across the Atlantic, and then encircles Iceland, bringing the ocean temperature up by 4 to 5 degrees. So that is superimposed on the effect of the sea that would else be here, because it's much warmer. But there is another factor that is affecting the climate in Iceland, and that is that Iceland is on the boundaries between the northeasterly and southeasterly winds. This boundary shifts south in winter and north in summer, but even though the boundary is a little bit south now, so the northeasterly winds should be dominant, we have another phenomenon, that is that we have a low pressure system arriving from the south, bringing warmth, heat, and they travel along the boundaries. So ahead of like a wave. So ahead of the wave, you will have a lot of precipitation and some warmth, but then inside the wave, there will be much warmer air. And we were inside the wave today. Now we are behind the wave. So now the northeasterly winds will be more effective than they have been today. But still, since it's a low pressure system, the wind will circle around it. So some of the air masses actually come from the south and blend with the northeasterly wind. So it's relatively warm. Just for comparison, the middle of Alaska is between the 64th and the 66th parallel, and it's definitely much colder there today. Sometimes even the weather in Reykjavik, the capital, will be warmer than London or Paris during the winter. So we have an ever-changing weather, and there is a saying, if you don't like the weather, why don't you wait an hour or two? It will change. And you can have rain in the morning, sun in the afternoon, and then snowing during the night. That's quite common. Like I told you, we are heading eastward. We first have to drive a little bit north before we turn off the ring road, road 1, that then circles the island, and go straight east to Þingvellir, Parliamentary Meadows. This is a national park today. It is a site of Icelandic Parliament, founded in 930. And this was the site of Parliament until 1800, when the Parliament was moved to the capital, Reykjavik. So all through these centuries, that's where people met. The Icelandic Parliament was, like I said, founded in 930. It was a Commonwealth Parliament, which means that it was not just a legislative body, it was also a judicial body. You can find remnants of this in two countries on either side of Iceland, the United States and Britain. In Britain, the highest court of the land is in some cases the House of Lords. Some cases have to go to the House of Lords, and when House of Lords comes into session addressing these issues as a judiciary body, that is the only issue on the agenda. The same with the Senate of the United States. If there is a session deciding on whether to depose a judge or impeach a president, the only body in the land that can do so is the Senate, and this will be the only issue on the agenda at that particular session. The Icelandic Commonwealth thus had a parliament with both legislative and judicial power, but there was no executive power. If you had a judgment that went in your favor, to execute it you had to do it yourself with the help of your friends or family, if the other party was not willing to abide by the judgment. Iceland did not have an executive power until 1262, when Iceland became a state under the Norwegian king. Separate state, not part of Norway, but still with the same king who had executive powers. I want to bring to your attention that the skies are clearing. I see a few stars. Let's be in a positive frame of mind and have them clear somewhat more. I want to enlist everyone on this bus as my lookout, especially the people on the left-hand side by the window. They are favored on this tour because we are heading east, and the northern lights will most likely appear in the north. That happens 90% of the time. So you are favored people, so you will be my best lookouts. And then a little bit about northern lights. What are the northern lights? How are they formed? What creates them? For this I will need to take you back to Physics 101, addressing the question, what is light? How is light created? If you remember the atomic model of Niels Bohr, the Danish physicist, he described an atom as a core of protons and neutrons, and then with some swishing electrons around that core. But the electrons could not swish wherever, they only swished in certain spheres at a certain distance away from the core. The sphere closest to the nucleus of the atom had the least energy, and the further away from the atom the higher the energy level of that particular sphere. So now we have these electrons switching around, and then something happens to the atom. There is a transfer of energy into the atom, and the only way that the atom can respond is by bumping some of the electrons up to a higher energy sphere. It's a reflex. Can't control it. That's the only way it can react to this extra energy that has been transferred into it. It doesn't have a choice in the matter. This is the law of physics. But this is not a stable state for this particular atom. So it will tend to have the electron that was bumped up return to its natural state, to its stable state. And the only way that an atom can do that is when it brings down the atom to its stable state, the sphere it should be at, it gets rid of the extra energy by emitting light. And it's the only way it can get rid of that energy. So light is energy, and it's created in this way, and only this way. So back to the northern lights. If we go back about 13.5 billion years, that is the estimated creation of the universe. 4.5 billion years, the creation of our solar system. And when our solar system was created, most of the hydrogen atoms in the system congregated towards one point, creating the sun. But when all these atoms were in such a cramped space, they started to fuse. By that I mean two hydrogen atoms came together, creating one helium atom. It's a different element. And when this fusion took place, there was a lot of energy left over, mainly in the form of heat. So the fusion created loose energy, leftover energy. And this is a process that has been going on for 4.5 billion years, and it will continue to go on for more than 4.5 billion years, according to the scientists' calculations. So now you have this fusion, and it's continuous, so a lot of heat is let loose there. There are other forms of the energy, but mainly it's heat. And this will heat the sun more and more. But when the inside of the sun reaches 14 million degrees centigrade, that's about 27 million degrees, just over 27 million degrees Fahrenheit, the sun can no longer contain all that heat. It cannot contain the energy that's let loose. So it has to get rid of it. And it does so in many ways. I'll name but three. The first one, the least energy intensive, are very small particles, subatomic particles. They are called mesons. And they burst out of the sun, and they travel close to the speed of light. And they pass through matter, because most of the matter is really empty space. Some of them have passed through your body today. Most of them have passed through Earth on their way away on their route away from the sun. The second form of energy I want to talk about are the electromagnetic waves. The spectrum runs all the way from gamma rays through X-rays over to the other end where we have the long radio waves. But towards the middle, there is a part of the spectrum that we as humans can appreciate. Every day we appreciate the light from the sun, daylight. And we have a specific sense, our vision, to appreciate it. with our eyes and the interpretation in the brain, we sense light. But there are other two parts of the spectrum that we can appreciate, and the reference is always the visible light. So we have the infrared and the ultraviolet on either side of the visible light. If we are out in the sun, we can feel the heat of the sun on our skin. This is the infrared part of the spectrum. And if we are long enough out in the sun, our skin will turn a little bit darker. That is the ultraviolet part. So we have adapted to our environment, and especially in this instance, the sun, by developing the sense of vision, the sense of heat, and the reaction of turning our skin a little bit darker to withstand the onslaught of the sun rays. Now I come to the third form of energy that the sun exudes. They are really in two forms. One is created and how do I put that? It's organized by the magnetic field of the sun, and they are called solar flares. And you can see them if you hold a disc that is equal to the size of the sun, according to your eye, you will see that there are some light loops that stem from the surface and return to the surface. It's like a loop of light. These are the flares. This is really created by the extra energy inside the sun, directed or organized by the magnetic field. So they shoot up away from the sun, but the magnetic field draws most of it back. But a little bit of them escape and travel away. So the sun has got rid of a little bit of energy with the flare. But the greatest exude of energy from the sun happens when the temperature has reached such a level that the surface of the sun can no longer contain it. And this happens about 14 billion degrees centigrade. And then there is a rupture in the surface. And outstream billions of tons of electrically and magnetically charged particles. They will travel away from the sun in a direct line. Since man has now satellite in space, man has been able to monitor the sun. It monitors many parts of the electromagnetic spectrum, among them visible light. And when there is a dark spot on the surface of the sun facing Earth, that is interpreted as a rupture, and it's called the corona. And outstream these billions of tons of these particles. And they stream away from the sun, and if it's on the surface of the sun facing Earth, they stream towards Earth. This stream of these particles are called solar winds. But when they come up close to Earth, in the vicinity of Earth, they can no longer travel in a straight line, because the magnetic field of Earth thwarts them. So they will have to travel along the magnetic lines of the magnetic field and circumvent Earth. And that is really lucky for us, because otherwise we would not have any atmosphere. It would be swept away by the solar wind. This has happened to Mars. Mars had circumvented Earth and are traveling away from the Earth. Probably most of you know about magnets, that plate with magnets. So you know that you can never push together two magnets that have the same orientation, like they both have a North Pole on the North Pole or they both have a South Pole. You cannot push them together. If you push the North Poles together, it's impossible. But if you have one magnet with a North Pole orientation and one with a South Pole orientation, it's difficult to keep them apart. And if they come into close encounters with each other, they will go together because opposites attract. So now we have these particles. They have traveled along the magnetic lines and have now circumvented Earth. So they are in a position straight above the magnetic North Pole. And this is when the law of attraction comes into play. The North Pole will attract those particles that have a southerly orientation. So they will decelerate, and then they will start to accelerate in the opposite direction towards the magnetic pole. And this is where they can enter the atmosphere. So what happens there? There will be encounters with atoms in the atmosphere, collisions. And these collisions will transfer energy into the atoms of the atmosphere. This starts to happen about 300 kilometers up, but most of the particles travel further down. But about 100 to 150 kilometers up, that's when most of them will collide with atoms of the atmosphere because of the density of the atoms is such that they cannot pass through. And now we come back to physics. What happens when there is a collision between matter and an atom? There's an energy transfer into the atom. So many, multitude of atoms become excited. That is, their electrons are bumped up to a higher energy swell. But this is not the stable state. So what happens then? The atoms will tend to return to the stable state, moving the electrons down to a lower energy sphere and thereby emitting light, creating northern lights. So now everybody knows how northern lights are created. There are really two key parameters for seeing the northern lights. That there was a solar wind that has originated a day or two ago, and we had knowledge of it, so we can estimate when they will reach Earth, when the wind will reach Earth, and we need preferably clear skies, but at least an opening in the sky big enough for us to see the return of the electrons to the stable state, creating the northern lights. The light from the sun travels in about 8 minutes, but these particles, they take a day or two to travel to Earth. The light has a speed of 300,000 kilometers, but the particles 3,000 kilometers or below. A second. Still very fast, but not very fast compared to light. So now we have the satellites in space. They monitor the surface of the sun facing Earth. The size of the corona will be indicative of the power that's being released, the energy release, and So the weather was not our friend tonight. Now it's snowing, but I did explain maybe a bit about the Icelandic weather system here. Being an island in the middle of the ocean affects us. And then the northeasterly and southwesterly winds. So the weather changes rapidly. We will be heading back to town now. Please come another day or another evening. You can come any evening where we have trips until early April. And then you can come next winter from late August till beginning of April in 2019. And then you can come again in 2020 until April. Okay? But if you're staying, please check with Grey Line tomorrow around 2 o'clock and see if they are going to go on an excursion hunting for northern lights. Okay, everybody please fasten seatbelts.